Hi everyone, this is chapter 2, electric field. You will see in this chapter the concept of electric field is really similar to the concept of the electric force. In fact, it is simply the electric force divided by the charge we will be calculating the force on. Okay, what do I mean by this? Let's say we have a point charge and we want to calculate the force at point P. What we could do is calculate something that's called the electric field, so the electric field from this charge at point P, and then multiply the charge we want to add at that point to get our resultant force. Therefore, the electric field is simply electric field vector is equal to the Coulomb constant multiplied by the charge that is creating the electric field, in this case it will be that charge, divided by r squared. Now note, if we wanted to calculate the electric force will simply be equal to Q2. Q2 in this case will be the charge that we are adding, let's say at point P, multiplied by the electric field. Okay, so it's a really simple simplification, but you will see in chapter 3 and 4, it's simplified greatly the mathematics needed to solve some of the problem. So the concept of electric field, even though it is simple in terms of the electric force, it is a very useful concept. One of the concepts that is tied into the electric field is the concept of electric field line. So let's imagine that we have a positive charge. So from the point of view of an electric field, a positive charge will be emitting electric field line outward. And the bigger the charge, the more line it will be emitting, all right? The reverse concept is true for a negative charge. So a negative charge, instead of emitting electric field line, it will be absorbing electric field line. And again, if it's a bigger charge, it will absorb more line. Now, these concepts really they will be used mainly in chapter 3, and with some example it will make more sense, okay? But for now, just think that positively charged particle emit electric field outward, negatively charged particle absorb electric field line. All right, we will come back to this concept in chapter 3. Another concept we need to talk about is the concept of charge density. So let's imagine that we have a marker here, and let's say it is positively charged. So let's have a positive charge, but we don't know the total charge on my marker, but maybe we know the amount of charge for every meter of the marker. Well, if we know the total, the number of charge for every meter of the marker, we can simply multiply by the length of the marker and get back our total charge. So, as you've seen in the note, when we are talking with a linear charge density, so a charge density with respect to the length, we're using the symbol lambda. And we can find the total charge, by multiplying this lambda by the length. Now in this course, we are only going to consider charge density that are constant throughout the length of an object. The charge density won't change depending on where you are on the object. This will simplify the calculation. Now, when we are considering the linear charge density, so it's the charge density in one dimension, we have the same concept in 2 dimension and in 3 dimension. In 2 dimension, we use the letter sigma. So sigma is the amount of charge per meter square. If we want to get the total charge, well, we multiply sigma by the area in meter square. Sigma multiplied by area, and we get our charge. And again, we have the same concept in 3D. Now it's the volume charge density. We use the letter rho, and the letter rho represents the amount of charge per meter cube, all right? So if we want to get the total charge, we multiply rho by the amount of meter cube we have in our object. So rho multiplied by volume is equal to the charge. The last concept we need to cover before we start solving some example in this chapter is the electric field near infinite plane. So what I mean by that, let's say we have a piece of metal, or a big sheet of metal, that is charged. It is possible to calculate the electric field near the plate. And although we will need to use calculus to get this value, and I don't intend to do the complete derivation, it will take a while, and from experience, all my students are falling asleep every time I do this demonstration. So what we can conclude though is near a big plate that is charged, or a surface that is charged, we can find the electric field to be constant, and E is equal to the surface charge density divided by epsilon zero. Epsilon zero represents the vacuum permittivity. So it's the ability of the vacuum to enable electric field to travel. All right. Epsilon zero is equal to 8.854 multiplied by 10 to the power minus 12 farad meter. We will talk about the unit farad in chapter 5. For now, it does not really matter. Only this value really matter. Now again, especially for point 2, 3, and 4, they will be used more in the next chapter, and it will make more sense once we solve some example. All right, so let's go solve some example to make more sense of all these new concepts. All right, so see you in the next video.